So the course is fundamental to composites and cellular materials. And if you have any query, if any student or anyone is online, please, you can ask your questions to the YouTube channel, and we'll be happy to answer your questions. Can you see anyone available? One watching now. Who is one watching?
We get the ones. The main detail data.
Right. Just to muted. Yeah. Okay. So once there. So what happens? This one gets recorded, and it remains there online, huh? Okay, so no, very much, very muted. So as we understand, I understand that whatever we say here, it gets recorded and uploaded. So let me say a few things here. In the last two sessions, we talked about the basics of composite materials, their classification, cellular materials, their classification, how do you choose different matrix and reinforcement materials, how do you combine them. We talked about mechanics, we talked about synthesis of fibers. So the next classes, if we have gone through, we have classes on synthesis of, and before that we talked about the interface also. So the interface in metal matrix, interface in ceramic matrix, and how do you engineer the interface? All those points we have discussed briefly in the last two sessions. If you go through the codes, you'll be seeing in the later stage, we have the different synthesis topics. For example, synthesis of metal matrix composites, synthesis of ceramic matrix composites, synthesis of cellular materials, right? So, and if you have again gone through the lecture on metal matrix composite synthesis, you'll be seeing there are a gamut of different synthesis techniques have been discussed. And the basic idea here, if you have noticed, there are three basic underlying features. One is that you want to have homogeneous distribution of the reinforcement particles. But the major problem in melting casting route is that the density difference between the matrix and reinforcement particles are always quite high, and that leads to segregation. So you must have noticed one of the idea or one of the innovations in these processing techniques, or one of the modifications in these processing techniques, is that how do we actually get rid of those kind of segregation and we get homogeneous distribution, number one. Number two, in a molten matrix, in a molten system, when you add some solid particles, the viscosity increases, right? And that leads to issue with wettability. And in the chapter of interface, you have learned that, so I will call it, I'm talking to call course, please, eh? And you have noticed that wettability is a very important factor in interface. You need very good wettability. So just to go back, if you want to have good interface cell adhesion, 2 points are of paramount importance. One is definitely you need to have excellent wettability. So that means you should have very good contact between the two surfaces. Secondly, the contact itself or having wettability is not the only factor. You also have to have very good bonding between the surfaces as well. So those points we have discussed in details in the interfacial phenomenon chapter. So we understand about wettability. Now coming back to here, when you load your metal matrix with certain volume fraction of reinforcement particles or fibers, the viscosity goes down, and that also affects the wettability. So first point I mentioned in terms of metal matrix synthesis, the first point which you need to take care, and in these different processes as we go along, starting from, if you remember, the first one is compo casting or Rio casting, and then from there we go to infiltration process, different kind of infiltration process. We go to squeeze casting, and then we go to spray forming. So and from the metal matrix, from the liquid phase, we go to solid state processes. So the basic idea here is to get extremely good homogenization of the second phase. And the second point is that also to achieve wettability, right? Because you have very good wettability. Now, the problem in melting route is that you have a metal matrix, you have a reinforcement. So there is always a chance of reaction at the interface. Okay. Until unless you really want that, in most cases, you don't want any kind of reaction to take place. In certain cases, however, obviously you want some kind of reaction, but in most cases you don't really want to have any reaction at the interface. That means you to stop that. But high temperature process, melting, the residence time is also high. Obviously, that leads to some kind of at least interdiffusion and further some amount of reaction as well. So now to stop that, what you need to do, you need to reduce the temperature. That means you need to reduce the the temperature of the melt or the superheat of the melt. Okay, that reduces viscosity, right? Also, you need to reduce the residence time. In compo casting, if you remember, the residence time is high. From compo casting, if you go to infiltration or squeeze casting, you have noticed that the residence time reduces significantly. So you can see all these processes, the way we have actually taught in this course is that there's a flow from, and the goal is that how do we achieve or how do we attain those few points to achieve good densification, to achieve good homogenization, to have good wettability, and also obviously to reduce the residence time of the particles in the melt. And obviously after the liquid phase processing or liquid state processing, we move to solid state processing, like we have roll bonding, we have powder metallurgy route, all those things we have discussed. So as I mentioned, ultimately the aim is to have very good distribution along with wettability and also reduced residence time to reduce the interfacial reaction. So if we have, in this concern, if we have gone through these few courses, few lectures on metal matrix composite materials, and if you have any query, we'll be happy to answer your questions. So with that, I leave to Professor Roy to say a few words.
Yeah, so thanks a lot, Professor Laha. So we also discussed a lot about the cellular solids. So to start with, already about the 2 or the 3 main classifications like open cell forms, closed cell forms, and honeycombs. We discussed about the various processing techniques of cellular solids. As you know by now, the cellular solids can be either metal forms, or they can be polymer forms or ceramic forms. And we discussed in detail how these various classes are fabricated. And we also discussed the various mechanical properties like the compression behavior of the forms, like the thermal conductivity of the forms. We discussed how, for example, the ceramic forms, for example, they are outstanding material for thermal applications because they are thermally insulating materials. At the same time, they have outstanding thermal shock resistance. These things we discussed. We also discussed about the energy absorption behavior in metal forms. we discussed about, for example, like this plateau behavior, typically like when you compress the metal forms, depending upon the density of the foam or the amount of porosity, we typically have three different regions, like the elastic deformation, then the plateau deformation and densification. So these things we discussed in detail. And we also discussed about various ways to measure the amount of porosity. That means we discussed, for example, this Archimedes principle, then the computer tomography we discussed about, then we discussed about this marker intrusion porosimetry. So all those methods, how we determine the porosity, these things we discussed. And towards the end of the course, we discussed about three special chapters where where we introduced actually three different cellular materials or kind of hybrid materials. The first one is wood. So as you know that all these woods or this kind of biological materials, they are actually cellular solids with a very defined structure containing a lot of pores, and the pores
Like
are not
pore as well.
exactly containing the pores, and the pores are also not isotropic. The pores are actually they are anisotropic, and depending upon the cell structure, how those lignins and all those materials they control the wood morphology and the mechanical properties. These we discussed in significant detail. And then we discussed about the human bone also. Like as you know, the human bone is not only a porous structure, it's a gradient porous structure. So by now, the definition of the gradient structure should be known to you. It basically means that in a gradient structure, the morphology and the composition and the properties are not homogeneous. Basically, along a particular direction or in a particular orientation, the morphology changes continuously, and that basically allows the specific properties to vary along a particular direction. For example, as we know, in case of bones, for example, we want the core of the bone to be as hollow as possible, because the bone should also be able to transmit the nutrients and all the fluids and all those things. However, as we move toward the surface of the bone, we actually have a more or less dense structure, because the bone is also a part of our muscular system, and they are the main load-bearing element of our human body. So this way, the bone is an outstanding engineering material, a natural marvel, so to say, which actually combines both cellular materials and composite materials or porous or solid materials in the same one with a gradient structure. And then in the last chapter, we discussed about the bulk FGMs or the functionally graded materials. So there we discussed about various methodologies through which we can actually fabricate the FGMs, how the properties of FGM vary from different materials, like the hardness, for example, or for example, the flexural strength, the conductivity, the expansion coefficient, the wear resistance. So how these things actually vary in a particular material with the function of with the kind of function of the distance or orientation. These things we discussed a lot, and we also introduced the various concepts of developing FGMs. We learned about the discrete FGMs or continuous FGMs, how they are fabricated, different fabrication techniques like SPS, hot press, centrifugal casting. So all those things we discussed in significant detail. And if you go through the slides, I have got one or two emails from you, clearing some of the questions. And if you have more queries, please feel free to send us queries, and we'll be happy to answer to your questions.
Right. So as I see, there is no other question so far. I think we can end the session.
Yeah.
So with that, I would again suggest that, whoever is watching this recorded video, please go through these different, lectures. The lectures are quite detailed, encompassing all kind of, synthesis of composite materials and cellular materials, their mechanics, selection of materials, classification, all those points have been vividly discussed in the different lectures in a chronological way. And we sincerely hope that it would definitely help the students as well as the teachers from the different state colleges and other researchers and scholars to help understand the subject, which is basically on hybrid materials, that is composite materials and cellular materials. We wish you all the very best. Would be extremely happy to receive any kind of feedback, questions, queries from you. With that, I, Tapas Laha, and my
Siddhartha Roy, we end today's lecture and all the best.
Thank you all. Have a very nice and happy puja vacation.
Thank you.
Thank you all.
Bye.